Hello, everyone. My name is Dr. Garrett Struckoff, and today we are going to be talking about aqueous chemistry. First, we'll cover solutions, aqueous and non-aqueous solutions, suspensions, solubility, calculating concentrations, a couple example problems, and then some practice problems for you to work on your own. So what is a solution? A solution is a homogeneous chemical mixture where the constituents have dissociated into individual ions and molecules. The major component is called the solvent. The minor components are called the solutes. An example that we've seen, I think almost all of us have seen in our lives, is salt water, like ocean water. The solvent is water. The solutes are the salt, sodium and chloride, and other salts as well. It is likely that every fluid you have experienced in your entire life has been a solution of one kind or another. Drinking water is not just water, it has other things in it, like calcium, magnesium, small amounts of chloride, and these are totally fine for us to drink. Gasoline is a solution. It's not a water-based solution. The solvent in that case is not water. But gasoline is a mixture of hydrocarbons. A lot of benzene, a lot of toluene, a lot of xylene. The air you breathe is a solution of elements and compounds. You might have thought that the air you breathe is somewhat like a pure element, but it's really not. The term aqueous describes a solution where the solvent is water. Aqueous comes from the Latin aqua, for water. Vinegar, you might not have thought about it, but vinegar is actually a aqueous solution of acetic acid. Soda, the kind that we drink, is a solution. Window cleaner, like Windex, is a solution, and it's represented as AQ in chemical equations. You can see on the right here, we have AQ in the chemical equation, and that tells us that silver and chloride, in this case on the left side, are both soluble. They're both solutes that are in the solution, whereas S over on the other side tells us that at that point, silver chloride has become a solid. It is no longer in solution, it's no longer aqueous. It is, well, actually a precipitate would be the term we would use. That said, there are very many non-aqueous solutions too. Olive oil is kind of a non-aqueous solution, other cooking oils as well. Tape residue, if you had some tape residue on a surface and you dissolved it with Goo Gone or a different kind of solvent, that solution that you maybe wipe up with your paper towel is still a solution. The tape residue is dissolved into the solvent. Motor oil is a solution, a non-aqueous solution. Oil-based paints, dry cleaning solutions, and nail polish and its remover are also non-aqueous solutions. Now, in contrast to that, a suspension is a heterogeneous chemical mixture where the fundamental particles are still chemically identical to the unsuspended material, meaning that it hasn't dissolved, it's just suspended. It's in the suspension, it's in the matrix. The matrix of the water. So wastewater, as an environmental engineer, we worry a lot about suspended solids in wastewater. That would be a suspension too. A colloidal suspension is a special case where the particles are so small that they cannot settle by gravity. Milk is actually a colloidal suspension. Polluted water can be a colloidal suspension. If you think about it, if you put milk out, well, if you leave milk in your refrigerator for a long time, it's still milk. It never separates into its fundamental particles. But you add a little bit of vinegar to it, and it starts to coagulate into something else. And then polluted water, if you have murky water, it's always going to be murky water, whether you let it sit for days or weeks or not. It doesn't settle by itself. A special type of suspension are emulsions. Not as applicable for environmental engineering, but some things like mayonnaise, butter, the way that soap works is actually an emulsion. It actually converts the bacteria and skin and oil on bacteria and viruses and oil on our skin into an emulsion that we can then rinse away. Each type of solution has a maximum concentration, and we call that the solubility. For example, table salt, regular sodium chloride, can dissolve to a maximum of about 360 grams per liter at 25 degrees Celsius. The Dead Sea, in comparison, is around 280 grams per liter. The saltiest body of water on Earth is around 280 grams per liter. So sugar, regular table sugar or sucrose, has a solubility much, much higher at 2,000 grams per liter. If you think about solubility, one thing's important to note, that it is temperature dependent. So you can see there for table salt, I put that it's 360 grams per liter at 25 degrees Celsius. And at other temperatures, that'll change. So at a higher temperature for salt, it's actually higher solubility. At a lower temperature, it's going to be a lower solubility. Silver nitrate and silver chloride, you can see the bullet point there, are a special interest to us because the nitrate version, silver nitrate, is extremely soluble, 2,500 grams per liter, whereas the chloride version is extremely insoluble, only 5 milligrams per liter. And that is actually used for mining. When they mine silver out of ore, out of rocks, they take the rocks, they mix them with nitric acid, which is, what's this? Nitric acid is hydronium nitrate, I guess you would call it. If you mix that with rocks, you dissolve the silver out of the rocks, and then you can add just a little bit of sodium chloride or some other kind of chloride compound, and it will actually precipitate all the silver out. And so you're left with pure silver chloride on the bottom of your reaction vessel. Compounds that are highly soluble in water are called hydrophilic. Those with low solubility are called hydrophobic. So water-fearing, hydrophobic; water-loving, hydrophilic. And like I said before, the solubility is temperature dependent. Salts are generally more soluble at higher temperatures. Interestingly, carbonates are actually usually less soluble at higher temperatures. And that has to do with the fact that carbonates are in equilibrium with a gas, carbon dioxide, and actually all gases, generally speaking, are less soluble at higher temperatures. So there are some properties of a solution in suspension. One is that the density is very close to the density of the solvent. If you have salt water has a little bit different density than fresh water. It's only because it's so concentrated. But most solutions, if we're looking at just a few milligrams per liter of a solute in the solvent, it's going to be about the same density as the solvent. Pure water does not conduct electricity. I don't know if you knew that or not. If you have actually pure just H2O, it will not. It is actually an insulator. However, it's also very easy to dissolve things into water that cause it to be electrically conductive. And so, yes, aqueous solutions generally have a pretty high electrical conductivity, and non-aqueous solutions tend to have a very low electrical conductivity. This is a reason why you don't really want to be in the ocean during a lightning storm or thunderstorm, because you might get shocked by the electricity traveling through the water. And then the spectral absorbance of light. The way that we measure a lot of compounds in the real world is by using either UV or visible light that we pass through a sample. And pure water does have an absorbance spectrum, and if you compare that to the absorbance of a different solution, you can actually calculate the concentration. I was actually just talking to some students of mine today about using absorption to calculate the concentration of algae in water. And so you might be able to pass light through and measure how much of the light is absorbed, and that can tell you the chemical concentration. The concentration of a solute is the quantity of the solute in a specific quantity of solvent. And there are many ways to measure this. We can use mass of solute and volume of solvent. We can use mass of solute and mass of solvent, maybe milligrams per kilogram. That's actually commonly used in soil too, actually. Volume of solute and volume of solvent, like ABV, alcohol by volume. Moles of solute and volume of solvent, molarity, and then moles of solute and total moles, which we call the mole fraction. We can convert from one to another using molecular weights and densities of the solute and solvent. And we also often use terms like parts per million, parts per billion. Generally speaking, parts per million is equivalent to a milligram per liter, and parts per billion is equivalent to a microgram per liter. And the reason why is because there are 1 million milligrams in a liter, which is basically the same as a kilogram of water. I have a couple of example problems for you. First, I put a large dose of sodium chloride into a 2-liter, 0.5 molar solution of silver nitrate. How much silver chloride will precipitate in terms of grams? So the first thing I need to do is think back to my solubility of silver chloride. And if you recall, I said a few slides ago that it is 5 milligrams per liter of solubility. So our solubility of silver chloride is 5 milligrams per liter. We can convert that into molarity. First thing I want to do, though, is figure out what is the molecular weight of silver chloride. So silver is 107.8 grams. Chloride is 35.5 grams. If we add those together, we get 143.3 grams per mole for silver chloride. So we can figure out our solubility by taking 5 milligrams per liter. We're going to use the factor label approach. 5 milligrams per liter, 143.3 grams per mole. We have 1,000. We have milligrams that we want to convert to grams, so we'll do 1,000 milligrams per gram. And that gives us the solubility of silver chloride, at least at this temperature that we're talking about, is 3.49 times 10 to the negative fifth molar. All right, that's kind of part of our answer, so we'll give that a dotted underline. We want to know how much mass is removed. We want to know how many grams of silver chloride is going to be taken out of the solution when we add chloride to it. So we started out with silver nitrate. We're going to add some sodium chloride. So how many grams of silver chloride do we expect to see? So we can say, because there's 1 mole of silver in silver nitrate, there's 1 mole of silver in silver chloride, we know it's a 1-to-1 ratio. So 0.5 minus 3.49 times 10 to the negative fifth moles per liter is the difference we'd expect to see. We started out with 0.5. And we know that when this reaction is done, let me finish 5 there. When this reaction is done, there's going to be 3.49 times 10 to the negative fifth molar. That will still be in solution. So that's just the solubility. So there will still be some in solution, a very small amount. And so we can say that our moles per liter, multiply that times 143.3 grams per mole of silver chloride, and then multiply that times 2 liters. And so moles cancels, liters cancels, and we're left with just grams, which is what we're looking for. And because the solubility is so low, essentially everything comes out of solution. So 0.5 minus 3.49 times 10 to the negative fifth times 143.3 times 2 gives us 143.3 grams of silver chloride as a precipitate. And then you could filter that out of the solution, burn it, you heat it up a certain amount, and it turns into elemental silver, which you can then sell, of course. For our last example problem, we have a 75 milligram per liter solution of NaCOOH. We want to find out what is the molarity of that solution. So the first thing to do is find out what is the molecular weight of NaCOOH. And that's going to be equal to the molecular weight of sodium is 23. Molecular weight of carbon is 12. 2 oxygen, so that's 2 times 16. Plus 1. And if we add all those up, we get that it is 69 grams per mole. All right. Now we can take our 75. Well, again, we'll use the factor label approach. 75 milligrams per liter. And just to be really clear, I'm going to go ahead and put that as milligrams of NaCOOH so I don't get confused. I know that there are 69 grams per mole, but I want to know that in terms of milligrams. So let's go ahead and convert this 1,000 milligrams per gram and the molecular weight of NaCOOH. We multiply that through 75 across the top, divided by 1,000, divided by 69, and we get 1.1 times 10 to the negative third moles per liter. You can see if we cancel out our units, milligrams cancels, grams cancels, and we're left with moles per liter, which we call molar. And like I said before, a couple practice problems for you to work on your own. You need to make a solution of 0.5 molar sodium bromide. You have a 250 milliliter volumetric flask and a scale accurate 10 milligrams. What mass of sodium bromide do you need to add to the flask to end up with a 0.5 molar solution? And the last question, in the previous problem, should you have been worried about the solubility of sodium bromide. Is it possible that you may have exceeded that solubility? Okay, that's what I have for you today. I hope that this was helpful. I know you'll be using this in your future classes, and I wish you the best.